Okay, so here we are. We have a frictionless pulley that we have mass 1 and mass 2 attached to. Mass 1 is hanging on this incline here. Mass 2 is hanging freely. And we have an angle here of 30 degrees. So what we would most likely be asked to do here is calculate the acceleration of the system. So most likely we would be asked to find the acceleration of the system. And in order for us to actually do that, I'm going to throw some numbers on here. And the numbers that we would need are as follows. We're going to need to know mass 1, let's say it's 2 kilograms. Mass 2, let's say, is 6 kilograms. We know the angle theta is 30 degrees. And then we are going to have friction in between these two surfaces here. So we're going to need to know the coefficients of friction. Let's say that mu static is 0.75, and let's say that mu kinetic is, I don't know, 0.25. And with these numbers now, there is a way for us to solve for the acceleration. What it's going to require us to do is think critically about these two objects and use all of the skills that we've gained thus far. So the first go-to we should always think of is drawing free body diagrams, and we're going to do that like this. I'm going to have, here is going to be mass 1, and here is going to be mass 2. Now mass 2 is the simpler one because it is free hanging, so this is going to be Fg2, and then up we're going to have the force of tension. Mass 1 is going to be interesting for the following reasons. First of all, the first thing always is that we're going to have some force of gravity, and that's always going to point straight down. Even if we're on an incline, gravity points straight down. Now let's think about what other forces we have acting here. So we have this rope, and that rope or string is going to provide some force of tension up and to the right. And then since we have contact between two surfaces here, we're going to have a normal force that's going to be up and to the left. Now we do have friction on here. And the question that we're going to need to ask ourselves is, what direction is this friction pointing? Because depending on what the system wants to do, the friction is going to act in a particular direction. So let's say that this force of gravity overpowers this component of this gravity so that the whole system moves in that direction. So if the system wants to move this way, friction is going to act against that motion and it's going to want to pull that way. Alternatively, if the system wants to move this way, let's say mass 1 is going to quote-unquote win and pull mass 2 up, which could happen. In this case, the force of friction is going to act, again, opposite the direction of motion, and it's going to pull in the opposite direction. Now, we don't know which way this system wants to accelerate yet, so we can't put a friction on our free body diagram yet. We will be able to in the future once we figure out what's happening. So let's continue. So our next step is going to be to draw our kind of extended diagram, right? Our little boxes inside of a dotted box. So we're going to have our box here, and here's our mass 1, and here's our mass 2. And what we're going to need is we're going to need to put all of the forces that are acting along the direction of motion onto this diagram. So quite obviously, Fg2 is going to be the first one we're going to put on here. So we know that Fg2 wants to pull the system along its direction of motion. Now on the left-hand side here, we need to be careful because it is not purely Fg1 that wants to accelerate this mass. So mass 1 wants to slide this way. So we're going to need to figure out what component of gravity is acting along the direction of motion, along that inclined plane. So if we draw our free body diagram with our forces, so this is tension, normal, and this is FG1. We're going to need to look at what the components of this are in order for us to determine how much of that gravity is pulling along the direction of motion. So we're going to use some trig functions, and since the angle is in here, that's where our angle, the angle of the incline is contained inside that little corner there. We want the opposite side, so we're going to use sine. So katoa, so opposite over hypotenuse. That means sine of theta is equal to the opposite side over the hypotenuse. So sine of 30 degrees equals opposite, and then our hypotenuse is FG, where if we multiply by FG on both sides, we end up with a thing. We've got red, black, please. FG sine of 30 degrees equals the opposite side. FG, and it's FG1 in this case, so we have M1 times G times sine of 30 degrees. M1 is 2 kilograms times 9.8 times sine of 30 degrees equals a number. It comes out to be a nice 9.8. Hooray for us. So we've got 9.8 newtons. And that is the amount of force that is pulling along the direction of motion. So that means we would have 9.8 newtons pulling in that direction. Now, another thing we're going to need to figure out, in order for us to determine which way this system wants to move, we're going to need to look at FG2. So FG2, which just correct. FG2 is going to be M2 times G, which is going to be 6 times 9.8, and that is going to be 58.8 newtons. So that means FG2 is 58.8 newtons. So what can we determine from these numbers? Well, we see that in terms of the acceleration of the system, there's 58.8 newtons pulling to the right and 9.8 newtons pulling to the left, which means that the system is going to accelerate in the direction of M2. So if we are to look back on our diagram where we had a block and a block, this is 1, this is 2, the system is going to want to accelerate that way. So if the system is going to accelerate in that direction, that means friction is going to be exerted against that motion, and it's going to be down into the left. So if we are to redraw our free body diagram, our correct free body diagram now for mass 1, now we're going to be able to complete it. We're going to say that I know this is Fg, this is the force of tension, this is the normal force, and now we have a force of friction acting in the opposite direction of the tension. So if we want to figure out the force of friction now, because we need to know how it's going to affect the motion of our system, we're going to use force of friction equals mu force normal. And the first question we're going to ask ourselves is, will this system move at all? Is there enough force to overcome the static friction? Before we can do that, we're going to need to figure out the normal force. And that normal force, if we go back to our free body diagram, right, if we draw our components here, we should know that this component right here is going to be equal to the normal force. So if that component is equal to the normal force, I'm going to need to use another trig function, this time the cosine, since this is the adjacent. So we're going to get cosine of theta equals the adjacent over the hypotenuse, meaning cosine of 30 degrees equals that adjacent side over FG1. And FG1, so let's multiply by FG1 on both sides. If we multiply by FG1 on both sides, we get FG1 cosine of 30 degrees equals the adjacent side. That FG1, of course, is M1 times G, and then that's cosine of 30 degrees equals that adjacent side. So M1 being, what is that, 2 kilograms? It's like a million light years away. Yeah, 2 times 9.8 times cosine of 30 degrees. And that number is going to come out to be 16, let's call it 17 newtons. So that means that our normal force is going to be 17 newtons. So from here, we're going to want to calculate the force of static friction and the force of kinetic friction. So the force of friction static is going to be mu static times normal force. So our force of friction static is equal to our mu static, which was 0.75, times the normal force of 17 newtons, giving us a force of friction static of 17 times 0.75, 12.75 newtons. So if we look back at our kind of extended body diagram, we said that we have 58.8 newtons pulling to the right and only 9.8 newtons pulling to the left. So 58.8 minus 9.8 gives us 49 newtons. So far, 49 newtons are being exerted in total towards mass 2. Mass 2 is winning by 49 newtons. So the most that static friction could apply is 12.75 newtons, meaning it is not enough to keep the object from moving. So the object will move. Right now, in order to determine what it is going to do when it moves, we're going to need to figure out the force of kinetic friction. And the force of kinetic friction would be calculated much the same way, where we would have the force of friction kinetic equals mu kinetic times force normal. So the force of friction kinetic is going to be our mu k, which was 0.25, times our force normal of 17 newtons, equaling, it is 0.25, right? And I don't want to mess it up. Yes, it is. All right, which gives us a 4.25 newtons. So now, if we're going to go back to our kind of funky diagram, we're going to see that we have mass 1 attached to mass 2. We said that there was, I'm going to draw my dotted line, we said that there was 58.8 newtons pulling this way. We had 9.8 newtons pulling that way, and now we know that there's another 4.25 newtons from friction. So if we're going to find the net force acting on this, to the right we have 58.8 minus 9.8 minus 4.25. That's going to give us a sum of the forces of 44.75 newtons. So that means our total force acting along the direction of motion is 44.75 newtons. So our last step would be, again, our goal here is to calculate the acceleration. So our acceleration is going to be the sum of the forces over the mass. In this case, it's the sum of the masses, since that force is trying to move two objects at the same time. We have 44.75 newtons over, we have 2 kilograms plus 6 kilograms, giving us 44.75 over 8, meaning the acceleration of the system will be 5.6 meters per second squared. And after much trial and tribulation, we have answered the question at hand. Now from here, it would be not trivial, but it would be the same exact process if you wanted to figure out the tension, where I would suggest using mass 2. Now that you know the acceleration, you can use mass 2 to figure out the tension. So we're running up on 5 minutes left in class. So what I'll do now is I will pause for any questions. Other than I have no idea what's going on. That's fine. I recorded this. I'm going to put up the notes on class notebook so you can watch this process back as many times as you need. But can I address any glaring, if I made an error, please let me know so that I can fix it. But now's the time to ask. Okay. Like I said, you're gonna. I would almost guarantee that you're probably gonna have to watch this back. That's fine. With enough practice, I think you'll be able to accomplish this no problem. So I'm going